Hello and welcome to this talk. The title is Java Language Futures. This is the full 2021 edition. My name is Gavin Bierman and I'm part of the Java platform group in Oracle. So in the next 30 minutes, I'm going to talk you through some of the exciting new features that are appearing in the Java language in the next few editions. I will be manning the Q&A window myself during the playback of this talk, so please ask questions as the talk proceeds and I will attempt to answer them all in real time. I just draw your attention to this safe harbor statement. This is a forwards-looking talk, so please bear that in mind and don't bank the future of your company in this talk. So Java is evolving rapidly. I'd like to report that we are keeping our promise of releasing a new version of Java every 6 months. Since Java 10 in March 2018, we've pumped out new versions of Java every 6 months, which is no mean task. And for those of us interested in language features, which I guess includes everyone listening today, it's been a productive time because we have new language features in every release so far. Now, we've adopted a strategy of releasing language features first as a preview, then in a subsequent release in a second preview form, and then in a subsequent release after that in a final form. So what we've managed to do is balance this very fast tempo with managing closely and carefully the design of and development of language features. I also want to point out that all the language features that we've released so far have been amended in some form in this process after discussion with our experts and our community. And of course, lots of changes have been made during the design process itself. And I think this demonstrates Oracle's commitment to the open development of Java. It's a real thing. So with that, I encourage you to take advantage of this process and get involved, because you can make a difference to the future of Java. Most of the new language features for the Java programming language come under the umbrella of the Amber project. Although not all, there will be some new language features coming with Project Valhalla, for example, but that's a talk on more realistically, many talks for another day. But most of the other features have come out under Project Amber, and you can take a look at this webpage at your leisure, but you'll see that we've been cranking out new features pretty regularly, as I pointed out before. The page has a goal of Project Amber, which is to explore and incubate smaller productivity-oriented language features. Now, I don't want you to come away with the impression that all the features are small, and this is not the case. In fact, many of them are actually quite large features, and we've adopted a deliberate policy of breaking up large features into smaller parts and releasing the parts slowly and incrementally. This has many advantages, including not overwhelming our developers with massive feature changes. And with these smaller changes, developers can experiment with them slowly. And it also gives us an opportunity to keep an eye on the progress of the design and make sure that these features are correct. Now, one of the big themes of our development of the Java language is pattern matching. And there have been several JEPs so far, 3. We've finalized one in Java 16. We have one in first preview form, hopefully in JDK 17 any day. And we have another JEP already out, which we're hoping to target in Java 18, but there are others in the pipeline too. Now, for the bulk of this talk, I'm going to discuss JEP 406, which is pattern matching for switch. which is the latest pattern matching feature under Project Amber. So it's going to appear in JDK 17 any day. I refer you to the fact that it has preview in the title. So this is a preview feature. It's in first preview, which means that it might change. And if you want to use any of these features, you have to use flags, both with the compiler and with the VM. Now, I plan to dive quite deeply into this new feature, not just because it's the latest thing and therefore very cool, but also because I think that this feature will actually start to unlock the power of pattern matching for the average Java developer. So hopefully by the end of this talk, you'll get a real sense of where pattern matching will improve your experience as a Java programmer. Now, before I go into these details, I wanted to make sure that everyone's kind of at the same page. So I wanted to do a little bit of revision, and I wanted to just go over some details of pattern matching in general, and also about switch, since this is about switch, just so everybody knows what it is that I'm talking about. So let's just quickly look at pattern matching as we shipped in JDK 16. So in JDK 16, in this JEP, we introduced the notion of a type pattern. The syntax is very familiar. So in the left-hand box here, syntax for a type pattern is an example, string S. So it looks very much like a variable declaration, which is not an accident. But the difference is in the semantics. So what is a pattern? Well, a pattern embodies a test, and pattern matching is the process of taking this test, the pattern, and matching it with a value. So in this particular case, string S is a test which checks to see if the value has the type string. Now, a match either succeeds or fails. And if it succeeds, so in other words, if the value is a string, then the variable S will be initialized with the string value. And where do you use one of these type patterns? Well, in Java 16, there's only one place to use it. We enhanced the instance of expression that already existed in Java. So on the right-hand side, instead of only being able to write a type, which is what you could do in Java versions up to 15, you can write a type pattern. So in this code at the bottom of the slide, I have an example. We're checking to see whether some variable O, let's say that's a type object, is an instance of, so whether it matches the pattern string S. So in other words, if it does match the pattern, then the instance of expression will return true. And therefore, in this case, the conditional statement will execute the then block. The process of pattern matching will, as I mentioned earlier, have initialized the variable in the pattern variable S. So you can use it in the then block. You see here I'm invoking the length method on the string. Now we made the compiler super smart about this sort of conditionality, the fact that a variable may or may not be initialized. So in fact, it's just not possible for you to use a pattern variable unless the compiler is certain that the variable will have been initialized. So in other words, the pattern match will have succeeded. So in this case, the compiler is sure that S will be initialized when you invoke the length method, because it's in the then block, and you can only have got there if the instance of returned true. Now, if you, for example, if this conditional had an else block, then you couldn't use S in the else block, because by the semantics, the only way to get into the else block is if the pattern failed to match. And in that case, of course, the variable would not have been initialized. In fact, the variable S is not even in scope in the else block. So we've made it very easy for you to avoid making mistakes. So that's what a pattern is. let's just quickly look at switch, and in particular switch expressions, which finalized in Java 14 in JEP 361. So here's an example. So I've declared an enum class weekdays, which has predictably 7 enum constants, Monday through Sunday. And here I have a statement, which is a local variable declaration. And the right-hand side of the declaration is an expression. And I'm using a switch as the expression. Now you can see that we're switching over the day, and depending on the value of the day, we return a value. And the value is, we have this new case label form with an arrow. And the right-hand side of the arrow is the value, an expression that will be the overall value of the switch. So for example, if the day was, say, Tuesday, then the overall value of the switch expression would be the value 7. Now, there's actually 2 additional features hiding in plain sight here, which are going to be important for things that we look at a bit later. So firstly, imagine that we commented out the case for Tuesday. In fact, the compiler at this point would signal a compile time error. And the reason for this is that this is a switch expression. An expression should have a value. And if the day was Tuesday, there would be no value to denote for the switch expression. Our feeling is that in those cases, if you'd written a switch like this, it was probably an error. You're not actually asking the language to throw an exception, and indeed, which exception would it throw? So in this case, we say that the switch expression is not total because it doesn't have a value for every case that you're switching over. So switch expressions have a totality requirement on them. The other interesting thing that's hidden here in plain sight is that there's no default clause here. And that's because the compiler has noticed that you're switching over an enum, and this enum has 7 enum constants, and you have a case for every one of them, in which case you are complete. There's no possibility of another value. So once it's seen all the values Monday through to Sunday, you don't need to write any more. So you don't need to write, for example, a default. And again, we'll see this in later slides. Another fact, just I'm sure you all remember, but a quirk of switch, both in expression form and in statement form, is that the expression that you're switching over, the selector expression, is restricted by type. So the expression must be either a char, byte, short, or int, or its boxed form, or a string, or an enum, and no other types. And we'll see, again, this will come up in a moment. So let's return to JEP 406, which is adding patterns to switch. So it's pretty obvious what we're going to do here. We want to add a new sort of label, perhaps we call it a pattern label, with our case. So instead of writing case constant, we can now write a pattern. So here's an example. We're switching over some object, and we want to say, here's the case, and the pattern is string s. So we've seen this pattern before. But immediately you can see that for this to work, we must have changed switch. The type of this selector expression is object. So for new style switches, so switches that use patterns, we have lifted the restriction on the type of the selector expression. It can be of any type. If we didn't do that, the patterns in a switch would be heavily restricted and not very useful. So now switch is much more powerful. You can switch over anything. Here's another thing that didn't occur in old style switches, but appears when we consider patterns for labels. So consider the first switch here. We're switching over some object, and we have a pattern labels string s and a pattern label integer I. So it's pretty obvious that these are completely distinct patterns. So you might imagine that they could occur in either order. Order makes no difference in this case. And in old style switches, order made no difference. But for pattern labels, where we have type patterns and we have subtyping, suddenly things are a little less obvious. For example, we could, if you look in the second switch here, we have two pattern labels, string S and char sequence CS. And recall that a string implements the interface char sequence. So if you had a string value, you might expect it to pick the first string and not match char sequence. But what if you wrote them the other way around? You wrote the char sequence pattern label first, as in the third switch here on the slide. Well, what do we expect the compiler to do? Well, we could ask that the compiler always picks the best one, and we push all of that extra work on the compiler. Now, languages that have attempted to do this, they typically run into problems. This is a very difficult problem when we come to more complicated patterns. So rather than do this, we are imposing an order. So the pattern labels are tested in the order that they appear. So in other words, if you had written the pattern labels in this order, where we've written the pattern label char sequence ahead of the pattern label string S, you can immediately see that there's a problem because the string S type pattern is never going to be matched because every string will match the char sequence pattern label. So we might say that the char sequence type pattern dominates the string S type pattern. So this is sort of dead code, and Java has always taken an opinion that dead code is a program error. And so in this case, if you write this code, the compiler will signal an error and say that the first pattern label dominates the second one, and that's an error. So you should write them the other way around. We can mix pattern labels with constants. So for example, here we have a switch, which if it is the constant string hello, the first clause matches, and otherwise all other strings will match the second clause with the type pattern string S. But of course, you can't write them in the other order for similar reasons that we saw in the previous slide, so, because here the constant label will be dominated by the string type pattern. Now, no language feature in Java can go without a discussion with the issues brought about by the null value, and pattern matching for switch is no exception. You will remember that currently in Java, if you switch over the null value, this automatically throws a null pointer exception, regardless of what you've got in the switch block. Now, our thinking is that once we have enhanced switch to include type patterns, this will not really be a sustainable semantics. It will be too complicated. So we are changing the semantics of switches with pattern labels. So not existing switches, they will stay with the current semantics. But if your switch has one of these new labels, we will not automatically throw a null pointer exception. We will have a look at the labels in the body. To help you, we are adding a new label, which is the null label. So in this case, if O actually has the value null, the first switch label, case null, will match. And we've also added a shorthand, which we discovered when we were playing around with early builds, that it was quite common that you wanted to group up the case of a null with the case of another type pattern. So for example, here, the second switch, the first clause matches if the value of O is either the null value or a string S. And in both cases, the S variable will be bound to either null or the string on the right-hand side of the arrow. You'll recall, I mentioned a little while ago, that switch expressions have this totality requirement where they had to be total. And we found in practice that this has been a great feature, right? Indeed, we've always wondered why we didn't do that in the first place for switch statements. Because the problem with switch statements without totality is it's very easy to get bugs where you're missing a case label and then the control flow just falls through the switch block and carries on having not executed any clause in the switch block. Now, switch expressions are required to be total for standard switches. And of course, we are going to enforce this for pattern labels too. So here we have a switch expression switching over an object, and we have two pattern labels, string S and integer I. And obviously those two together are not, this is not a total switch expression. There are lots of cases missing. So this will signal an error in the compiler, and you'll need to add, for example, a default to make it total. We have decided that for pattern switches, we will require totality for both the expression form, but also for the statement form, because it's so useful. So if you had written similar code as before, but using a statement, again with pattern labels only, this will also signal a compile time error. And the compiler will say that this switch statement is not total and you need to make it total. So of course, if you want it to just fall through, you just simply need to write default break. So it's not a huge hardship, but now the control flow is completely explicit, which is a good thing. You'll remember that we had this very nice feature with switch expressions that when you were switching over an enum, you only had to have case labels covering all the enum constants. Now it turns out with sealed hierarchies, another new feature that shipped with JDK 16, we have a similar property, but lifted up from values to types. So if we have a sealed hierarchy, say an interface S, with 3 permitted subclasses A, B, and C, that are, all 3 of them are final, then we know that any value of type S must be either a value of type A or B or C and nothing else. And in this case, if you switch over a value of type S and you have 3 type patterns covering types A, B, and C, then you do not require a default. The compiler is smart enough to see that your sealed hierarchy is completely covered by the type patterns. So that gives you a sense of the pattern matching for SwitchJet, but let me finish my talk by walking you through some of the things that we plan to add in JDK 18, 19, and so on. So I'm just going to give you a flavor of some of the features that we have in store for you. So so far, I've shown you only one form of pattern, that's the type pattern. In JET 405, we are proposing to add a new pattern form, which is called a record pattern. So record patterns, as you might guess from the name, are designed to match against values of a record type. So their test, the test embodied by record pattern, is obviously a type test that it's of the record type that you specify. But in addition, it's a structural pattern. It deconstructs the value and pulls the values apart. So imagine that we have a record class declaration of point with 2 record components, int x and int y. As we can create record values using new, so we can write, say, for example, new 0.34, we can match values of this record type using a record pattern, and this I've highlighted in the little box here. This record pattern asks whether the value E is of type point, and if it is, it would like to initialize the pattern variable x to the record component value x and initialize the pattern variable y to the record component value y as well. So it does two things. It both does a type test, and if that type test succeeds, it pulls apart the value and assigns the component values to pattern variables. Now this actually is a cool thing, but it's even more cool because we can nest patterns inside the record pattern. So here we have a slightly more complicated class declaration. We have a record class colored point, which contains itself a record class point, as well as containing a color, which is Nina. And now we can nest the record pattern for a point inside the record pattern for a colored point. So if you look inside this yellow box on the middle here, what test is this asking for? This is asking, is O a colored point whose first component is a point? And if so, then bind the pattern variable x to the x component of the point in the p component of the colored point, and so on for the y and for the color value. And so those variables are now free for you to use in the right-hand side of the case label. Now, just so really what we've got here is just how we can, similar to how we can nest constructor calls inside each other, you can nest patterns inside other patterns. And this nesting matches the depth of your object graph. So this should hint to you at some of the power that comes with pattern matching. It gives you a tool for navigating your object graphs and pulling out inner values. Now, my challenge to you is to write in Java. It's not very difficult, but write in Java, today Java, without these fancy patterns, the code you need to write to navigate through this little hierarchy. And you'll realize that instead of this, not even a line, one simple declarative statement of the pattern that you would like a value to match, you have to write a whole nest of boring conditionals forming navigation code, lots of boring checks about nulls, so you don't get null pointer exceptions. You don't have to do any of this with pattern matching. So it's a bit like the Sherlock Holmes story about the dog that didn't bark. This really is about code you don't have to write. And of course, we can drop some of these type declarations. You might want to use var, as we might expect. You might not care about some of the arguments, so we'll give you some form to say, I don't care about the y value in this case. We have similar other values. So for example, not just records, but arrays. We'd like to provide you, again, with a dual notion of how you construct an array value. So you create array values using these nice array creation expressions. And we would like to provide you with a simple pattern that both checks whether the value is an array. So in this case, in the box, it's checking whether the value is an integer array, but then it's also checking that it has two array components. And if so, it binds their values to the pattern variables I1 and I2. Now, if this, as I said, matches an array of exactly two values. If you would like an array with at least two values, then we provide you with this 3-dot form. And again, patterns can be nested. So here, we're checking whether the value is a point array containing 3 points, or at least 2 points, sorry, at least 2 points. And then we are deconstructing those 2 points to extract their x values using a record pattern. Now, that's for record values, for array values, but what about values of arbitrary user-defined classes? So here we have an example of a class for complex numbers, has 2 final fields, which are both private, and a constructor. So you build your values using a new expression, but we'd like to pull it apart. So we'd like to provide you with a means of pulling that value apart using a pattern. Well, for records and arrays, it's very obvious how to pull the values apart, but for arbitrary classes, it's very difficult. So we're going to have to provide you with a way of declaring it yourself. And we might, of course, constructors are not the only way to build values. We might construct values using builders. And so we're going to have to give you some way of pulling values apart using some pattern form of a builder. So let me wrap up. Pattern matching is often cited as one of the superpowers of functional programming languages, and we're bringing it to Java one piece at a time. You've seen type patterns, instance of with patterns, switch with patterns, record patterns, array patterns, arbitrary declarations of patterns for classes. And I hope this convinces you that Java is evolving fast. So please get involved.